Hey, hey, it's Dr. J, part 3 of section 4.6. This is the last portion of the material that'll be on the upcoming test. So today, we're going to basically use everything that we've learned. I'll just go ahead and start with an example. A bacteria sample contains 1,500 cells, and it doubles every half hour. Find the number of cells A after 80 minutes, B after 7 hours. Okay, so the key here is that it's doubling. Yeah, 1,500 cells is doubling. And it turns out that when we're talking about doubling, the original number really is insignificant, as we'll soon find out. So let's go ahead and start off with a model. We have the population of cells, or you could call it F. I'm calling it P. At time t is a constant times a to the t power. Very standard formula. You could also replace pt with y if you like. So the original amount, C, is 1,500. That's our initial population. And half an hour. So we have to decide how we're going to use the units of t. All right. Now you have choices. You could do it by minutes, and then t would be 30 minutes, or you could do it by hours. I'm going to go ahead and do hours. So that means t, a half an hour. T would be 0.5. I feel like we've done this problem before, but that's okay to do it again. And because the amount is doubling after a half an hour, then this amount is going to be 3,000. And here's where the 1,500 really becomes insignificant. What matters is that it's doubling. And so when something is doubling, you automatically, yeah, we've definitely done this before, but maybe I'll give it a little bit different treatment. This side becomes 2 all the time. So whenever you have a doubling time, this is always going to happen. You always end up with 2 over here, if it's doubling. Okay. Our goal is to solve for A. So we're going to take, well, let's just go ahead and square both sides. So that'll give us A is 4. This is A to the 1, yeah? 0.5 times 2 is 1. So A is 4. So our model now is that the population of bacteria, or the number of bacteria, you could use any symbol that you like. I'm counting the bacteria as if they were people. Is the original population times our base 4 to the t power, where t is represented in hours. Okay. So this is a base 4 model. basis 4. Let's go ahead and use this model to answer the two parts of the question. So we have two parts of our question, after 80 minutes and after 7 hours. So after 80 minutes, part A, 80 minutes, T would be 80 divided by 60, because there are 60 minutes and 80 minutes divided by 60 minutes per hour, which would be 8/6 hours, which would be 4/3 hours. Okay. I guess you could use a decimal, but it would be 1.333333, so it's better to use the fraction. So using our model, the population after 4/3 of an hour, or an hour and 20 minutes, would be 1,500 cells times the base 4 raised to the 4/3 power. So let's see, we've got base 4. If you like, you can break it up into steps. This is the cube root of 4 to the 4th. So we've got 4 to the 4th power. That's 256. And we'll do the cube root of that, which is 6.34. I'm going to write the whole thing down. 6.3496, blah, 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 blah. Then multiply that by, actually, let's raise that to the 3rd power to see if we get 256. Yes, we do. Go back to the cube root of that. So I should have 6.34. And then 3496, so on and so forth, times 1,500. 9524. Now, we can't have a fraction of a cell. We're assuming you either have a whole cell or you have no cells. So this is the approximate number of cells. You might as well round to the nearest integer after 80 minutes. For part B, 7 hours. Obviously, it's already in hours, so we can just do P of 7. We don't have to do this conversion property here. So we have 1,500 cells times 4 to the 7th power. That's going to be a lot of cells. So that's 1,500 cells times 16,384 multiplied by our 1,500 cells, and we're going to get a lot. I'll wait till I'm done writing it down to read it. So that'll be 24,576,000 cells. Last time I showed you how to convert your model to base E, if you like. There's some advantages to this. Let me first show you how it works, and then I'll talk about the advantages. So you have your, P of T is 1,500 times 4 to the T. You can convert that to base E. The constant remains the same. We saw that before. You change the base, but then you put a continuous growth rate That's what K represents. Continuous growth rate. As opposed to the hourly growth rate. Over here we have an hourly growth rate of 300%. But now I can turn that into a continuous growth rate just by setting these exponential pieces equal to each other and solving for K. Now, I do already have the answer. I'm just giving you an alternate way of resolving this problem. So you're going to have 4 to the t is equal to e to the kt. Or in other words, 4 is equal to e to the k. You could just cancel the t's here. We saw how that worked before. So you take the ln of both sides. You can see that ln of 4 equals k. And so your continuous growth rate is ln of 4. So that is 1.3863. I'm rounding to 4 decimal places. That's my continuous growth rate for K. You should get the same result using the continuous growth. Continuous growth, our model would be P of T is 1,500 cells times e to the 1.3863 times t. And we should get the same result. Let's see. So we have our exponent times t. We're going to do that times 4/3. So I take my growth rate, I multiply it by 4/3. That gives me 1,500 times e to the 1.84839, etc., etc. Then I do my exponential key e. I get 6.3496. And then I multiply that by 1,500, and I should get exactly the same amount, 9,524. I should get the same result. You can rewind and see if I did, in fact, get that same result. I sure hope I did. I'll check this one as well. P of t, so this is P of 4/3. Over here I'm doing P of 7. So I've got 1,500 times e to the 1.3863 t. I'm going to plug in 7 for t. So let's see. So I've got my 1.3863 to 1.386294361, or you can just round it to 4 decimal places. Multiply that by 7. So now look how large my exponent is, 9.70406, etc., etc. And then do e. You get 16,384. Does that look familiar? It's exactly the same value that we got last time times 1,500, and you get the same 24,576,000. I sure hope that's the same. Now I'm suspicious. You know, I've made a lot of mistakes lately, so let's check our answer. So let's just check this one. P of 7 was 1,500 times 4 to the 7th. 4 to the 7th times 1,500. Yep. 24,576,000. Check. Comes out to be the same. How about this one? P of 4/3 using the original base 4 model. Just double checking. So I've got 4 to the 4/3 power. That's 6.3496, etc., and then times 1,500, 9524. Check. So these should agree with each other. All right. So the key to this problem was the doubling time. Doubling time is an important concept in growth functions. When we talk about decay, we do it the other way around. A radioactive substance decays exponentially. A sample of 120 milligrams decays to 60 milligrams in 8 hours. How much of this substance will remain after 20 hours? And so if the amount of the substance decays to half, then this is called its half-life. So this time period is called the half-life. How much time does it take for the substance to get cut in half? It really doesn't matter that it was 120 milligrams. Had this been 500 milligrams, well then half would be 250. So if this value is cut in half, then the amount of time is called the half-life. And so you can see in your model that the amount that you have, A is the smaller amount and C is the larger amount because it is a decay function. So make sure you put them in the right position. A is 60 and C is 120. And then the amount of time is the half-life. And you will notice that the amount that you started with compared to the amount that you have is always going to come out to be 1/2 or 0.5. So this always happens with half-life. You can write it as 0.5 or you can write it as 1/2. It really doesn't matter. We still need to solve for A. I'm just setting it up here. So now we're going to solve for A. So we're going to take the 8th root of both sides. So we've got 0.5 eighth root. So A comes out to be 0.9170. So now our model, the amount after a period of time t, I like to write as a function, is the original amount, 120 milligrams, times 0.9170 raised to the t power. So the question is asking us how much will be left after 20 hours. So now we're going to plug in t equals 20 and put it into our calculator. So we have the amount after 20 hours Well, I like to just keep this number on my calculator screen. So I've got the base on my screen. I know I rounded it for, practical purposes, but when you're calculating, I like to just leave it on there, raise it to the 20th power. You're going to get 120 times 0.176776695, and then multiply that by 120, and you're going to get approximately 21 milligrams. If I've done that correctly. 21.2, I'm just rounding to the nearest milligram. You should round as directed. So read the instructions carefully. I like to just go to the nearest milligram, but I don't know what the particular question that I might pose will ask. So again, this is not a natural base. This is base 0.9170. It's a sort of a strange base. You might want to write this using base E. It might be something that will be asked of you, or it might be something that you find easier. It might be a more natural way of solving the problem. So you can also use base E, the natural base. So again, let's do it. We have the same basic idea. We want to convert to natural base. Remember, the constant doesn't change. What changes is the exponent. When you have this 0.9 base, your exponent is just t, but when you have the natural base, you get your exponent is kt. Let's keep our answer here, and we'll compare that we should get the same answer. So I'll leave that there as a check. Last time I erased it, I had to go back and find it again. Okay, remember the constants will remain the same, so you just take the bases and set them equal to each other. These are both raised to the power of t. Yeah. I didn't really do this last time, but I guess if you really want to, you're taking the teeth root of both sides. So those cancel out. And so you end up with 0.9170. Last time I just said cancel out the t's. I thought that might be clear, but just in case it's not clear, you're taking the teeth root of both sides. T is arbitrary. And so you're really just trying to figure out what k is. And you're going to take the ln of both sides. And that will tell us what our K is. Interesting note, this should be ln of 0.5 divided by 8. Let's just compare that that is true, because you might want a general recipe. So 0.5 ln divided by 8 is negative 0.08664. I'm going to write the whole thing down for now. I want a good comparison. Let's do it this way. 0.9170 ln. What do you know? This is the same value. So these should be the same value. So if you like to memorize half-life, K is equal to ln of a half divided by the half-life. This is the continuous decay constant formula. So some people just memorize this formula. These always come out to be the same. So you could do ln of 0.9170, or you could have done ln of a half divided by 8. These are the same thing. They come out to be the same value. So now we have a continuous growth formula here. So our continuous growth formula is AT is 120 times e to the negative. I'm sorry, I just said growth. I'm talking about decay. Continuous decay formula, 0.0866 t. 4 decimal places is sufficient for this problem. We were going to check whether or not we actually got 21 milligrams. Let's see, what was it, 20 hours? We should still get (21 milligrams after 20 hours. Let's see. So we have, I don't know why I cleared it out. I should have kept it there. 0.086643398 negative, and then we're going to do multiply by 20. Multiply by 20 first. So when you multiply by 20, you're going to get negative 1.73286, etc., etc. Then you're going to do your exponential, 0.176776694, and then you're going to multiply by your 120 original sample, and you're still going to get 21 milligrams. Check. So it checks out. Okay, example 3. Suppose we have an unknown radioactive substance. An initial sample decays, excuse me, let me use a better word, decreases by 8% 4 days. Find the half-life. So part A, find the half-life. Part B, how long will it take for 50 milligrams of this substance to decay to 5 milligrams. Okay. So we have that it's decreasing by 8%. So 8% of it is disappearing. So that means that 92% of it remains. So when we do our model, I'm using the algebraic model. The amount that remains is going to be 92% remaining from an original 100% in 4 days. So I'm going to let T represent days. So T is equal to 4. Okay. So if it's decreasing by 8%, that means that 92% is remaining from an original 100%. You could actually skip this step because you know that when you divide by 100, you're just going to get 92% is a to the 4th power. So you could just jump from 92% directly to 0.92 and skip the step of dividing by 100. I like to do it because I like to actually see the original 100% and then the remaining 92%, and I can confirm that that has in fact decreased by 8%. Now we could take the 4th root of both sides, and that will give us our A. I know, I don't really have to show this step, but I'm doing it anyway. So we get our A is approximately 92%. The 4th root is 0.97937036. 9793736. Okay, good. All right. So that's our algebraic base. That doesn't tell us our half-life, though. In order to do our half-life, we would have to take our model, use our new base, and solve for T, where A and C define the half-life. A should be half of C. So whatever C is, let's just say C is 1, then A would be 1/2. Or you could say 0.5. So this is how we solve. This is one method for solving for half-life. So now we're going to take the ln of both sides, the natural log of both sides. And you know where to go from here. Same step as always. You're going to bring your exponent down to the front. There's our t. And we're going to divide both sides by t. So I've got, I'm just going to rewrite it like this. T times ln of 0.9793736 equals ln of 0.5. Just rearranging the order, just makes it look a little nicer. Let's go ahead and use our calculator now. So we've got ln of 0.9 is negative 0.020845402. Might as well write it all down. And then ln of 0.5, you recognize this, it's negative 0.69. This is my next part, so I'm going to hang on to this. Negative 0.693147181. You probably recognize that. It comes up a lot. And then now we're going to divide both sides by this constant. And that should give us our t for the half-life. So we've got this decimal. I just kept it on my screen, and then I'm going to divide by 0.020845402, negative, of course. So negative divided by a negative, going to give us a positive 33.2518, or you could just say 33 days. Keep in mind, we're measuring with days, so your t, whatever you pick at the beginning to be your time unit, that's what your answer is going to represent, so 33 days. So the half-life of this substance is 33 days. Now keep in mind what the half-life gives us is what we call the natural model. The natural model, the amount at a time t is the original amount times e to the kt, or you could use the other notation, what was it? The mass at time t is the original mass e to the kt. It doesn't matter. These formulas mean the same thing. This would be the function notation using a for amount. And this would be the subscript notation using m for mass. Amount, mass, it really makes no difference. Okay, so remember, K is the continuous growth constant. That will be ln of a half divided by the half-life. So K is negative 0.693147181. That's the ln of a half. I don't have to do it again. We already know it. Divided by 33. So ln of a half divided by 33. This is a decaying element, decaying substance, so it better be a negative constant. 2100446. So this is our continuous decay constant. Now I can use this model to answer this question. How long will it take for a mass, I guess I picked this model, to decay to 5 milligrams? I didn't give any specific instruction on where to round. If I do, then follow the instructions. I prefer to keep all of my decimals until the very end, and then I can always round later. So remember, the original amount now is 50 milligrams, so that's my M0, my initial mass, and then my mass at time t, MT, is 5 milligrams. Make sure you put these in the right order, otherwise your answer won't make any sense. And you're going to solve for t here. So we're going to divide both sides by 50. We're going to get 1/10. Again, what's the benefit of using the natural exponential model is that when you do your ln, I'm just going to write 1/10 as 0.1. When you take the ln, it automatically cancels the e. And it makes your equation very easy to solve. Now you just divide both sides by this coefficient, and that should tell me the time required. So here's my t, dividing both sides. So what do I got? I got ln of 0.1. ln of 0.1 divided by 0.0200446 negative. So that comes out to be 114.8 or 115 days. So the answer is approximately 115 days. For a question like this, I would just have you round to the nearest day or as indicated. All right. Okay, example 4. We have another one of these bacteria problems. This time we are not given the doubling period. Our objective is to find the doubling period. We're given an initial sample containing 3 cells. So let's give that a label. Let's call that n sub 0. That's the initial number, n sub 0, the number at time 0. After 30 minutes, so that's our t, 30 minutes, the number of cells had grown nt, the number of cells at time t came out to 24 cells where t is equal to 30. Okay, so let's start off by finding the doubling period. We have our model. Our growth model will be n of t is n initial times e to the kt. That's our natural growth model. It's also part of part B is asking us to find a base E growth model. So we're killing 2 birds with 1 stone here. Notice part B is asking us for hours, 2 hours. But our problem is given in minutes. So we have a very important decision to make. If we do minutes, well then 2 hours would be 120 minutes. Or if we do hours, then 30 minutes will be half an hour. The choice is yours. But once you choose, you may not like your choice, but you've made it. So, I always call that, you made your bed. I'm going to go ahead and choose t to be hours. And therefore, 30 minutes is 0.5 or half an hour. Okay, so now I've made my bed. Let's go ahead and plug everybody in. We've got 24 cells. That's our MT. Our initial sample, N sub 0 is 3. E to the K. And since I chose 30 minutes to represent time in hours, 30 minutes is half an hour, 0.5. We're going to solve this for K. That's going to tell us what our continuous growth constant is. Take the ln of both sides. I probably don't need to show this step, but you know, when you take the ln of E, that's going to become 1. And this exponent is going to drop down to the front here. So now we've got ln of 8 is equal to 0.5k times ln of E. You know that ln of E is 1. So you can just cross it off, or you could write 1 if you like. And then you're going to have ln of 8 divided by 0.5, and that's going to give us our k. Just dividing both sides by 0.5. All right, so this is our continuous growth constant. ln of 8 divided by 0.5. It's 4.15888. So we'll say 89. We'll go ahead and go to 4 decimal places. All right, now that's not the doubling period. We can use this to find the doubling period. D for doubling period. So if you remember the formula, the doubling period K is equal to ln of 2 divided by D, the doubling period. D for doubling. Okay, and we're going to solve this for D. You know what I like to do is I like to just solve it algebraically and then plug in the numbers when I'm done. So let's multiply both sides by D. We get dk is ln of 2 and divide both sides by k. And there's your formula for doubling. Ln of 2 divided by k. So we got ln of 2 divided by k, so our doubling period is ln of 2 divided by 4.1589. Now I still have the entire number on my calculator, so I might as well use it. It's actually 4.158883083. The more digits you use, the more accurate your result is going to be. So I'll do ln of 2 divided by, and I get D is 0.1666666, which is 1/6 of an hour. 1/6 of an hour. That's our doubling period. Did you recognize that? 0.1666666. If you don't recognize it, just look. 1 divided by 6, and what do you get? 0.1666666. That's 1/6. It's also half of a third. In terms of minutes, the doubling period would be 10 minutes. One-sixth of an hour, which is the same as 1/6 of 60 minutes, which is the same as 10 minutes. So why am I giving you two different answers for Oh, here's my K here. Better hang on to that. Giving you two different answers for the doubling period. It just depends on your choice. Remember, I said it was your choice. In this particular problem, hours or minutes. You could measure T using hours, or you could do minutes, and it is your choice. But once you've made your choice, you made it. So at this point, I'm just going to go ahead and round this value. It's just a lot easier to write down the K because I'm about to erase my calculation here. I want to know how much I have left after 2 hours. So that's part B. So this is part A. Part A is now done. So for part B, I've got my model. The amount, the number of cells at time T is going to be my original 3 cells times e to the 4.1589 t. So now I can plug in any value for t. And that's where this choice here is so important. I chose hours. Yeah, so my answer would be 1/6 of an hour, or 0.1666666. Had you chosen minutes, well, then you would have a different value here, and you'd be plugging in the number of minutes. Since I chose 2 hours, I chose hours, I can just plug in 2. So the number of cells at 2 hours, I'm plugging in 2 for T. If you chose minutes, then you'd be plugging in 120 for T. So I've got my K, 4.1589 times 2 hours, and then e to that power. So that's 4,096. Now there are some decimals, but I'm going to be rounding to the nearest cell anyway, and then multiply that by 3. So the number of cells after 2 hours rounded to the nearest cell is 12,288 cells after 2 hours. Okay, so that's the bacteria problem if you are not given the doubling time. So there's a little bit more work to be done there. Example 5. A mummy was discovered in a tomb. After sampling, it was found to contain 15% of the original carbon-14, also known as C14. Now I'm assuming of a living human. So we know approximately how much carbon a living human would have when it's alive. They dug up this mummy, they sampled its skin, nails, whatever, and found that it contained 15% of the original carbon of a living human. How long ago did this person die? And then keep in mind, I'm going to give you the half-life for this problem. The half-life of C14 is 5,730 years. Okay, so we have the mass at time t would be its original mass. We measure carbon by its mass. E to the KT We know that it now contains 15% of its original. We'll just assume the original is 1. It's still alive. You've got 100% of your carbon when you're alive. Some number of years after you've been dead, you'll now only have 15%. And then we need to know what K is. Remember, K is ln of a half, because we're doing half-life, or ln, I'm just going to put 0.5. Just easier to write in this particular circumstance. Divided by 5,730. So that gives us our K, since we already know the half-life. So we got ln of 2. Excuse me, I hit the wrong button. ln of a half, glad I caught that, divided by 5,730. I'm going to get a very, very small decay constant, 0.001200968. That's the decay constant for carbon 14. So this K is going to go here, and we're going to solve for T. Remember, if you make a mistake and your constant comes out positive, it'll be growth, not decay. So make sure that you don't have the wrong sign for your K, because oftentimes these numbers look very similar. The only difference between growth and decay is whether or not the exponent is negative or not. We're going to take the ln of both sides. I probably don't have to show this step, but I'll do it anyway because I've got some space. The ln and the e are going to cancel. I could have just jumped right to this step. And now divide. So T is going to be ln of 15%, or 0.15, divided by negative 0.000120968. Don't round this number right away. If you're completed with the problem, or if the instructions tell you to round it, that's fine. But if you're just trying to find the solution to this particular problem, keep all of your decimals until the very end and do all your rounding in the very last step. Okay? So 15%, take the ln and then divide it by, let me go ahead and write this down in case I screw up. I want to have a record of my screw up. Send me an email if you find any of my screw ups. Divided by 0.001200968. And you're going to get T is approximately 15,682.8251, or I would accept 15,683 years. That's an old mummy. 15,000 years old. Okay, I'm going to go ahead and upload this. I do have 2 more examples that I don't have room to fit on this video, so I'll be posting those on a separate video. That's the law of studying and the law of forgetting. But I just want to get this one up there as quickly as possible. I've had lots of questions on it, so